Now we're going to talk about a very important application, which is nuclear medicine. So one of the most common applications for people to use radiation, one of the main ways that people are exposed to it is in medicine. And the two main applications are imaging and therapy. So when it comes to imaging, the reason why radiation is unique is that when a nucleus undergoes decay or undergoes some process where it emits radiation, it is sending a signal from inside the body based on the location of that nucleus. Okay? So those nuclei are in atoms, they're in molecules, and so what can happen that's unique with nuclear imaging, nuclear-based imaging, is that when these decay processes are happening, the molecule or the atom is explicitly sending a signal as to its location in the body, which allows for mapping of internal body structures. What does the brain look like? How much activity is going on in the brain? Where are the blood vessels? What are they doing, right? Because that signal is coming out explicitly from there. So one common type of imaging is positron emission tomography, which is also called a PET scan. And so in a PET scan, you have a nuclide that emits or that decays via positron emission, right? So you're going to get something with too many protons. You're going to put it in, and it's going to emit a positron out of that nucleus. And what ends up happening is we know that when that positron gets emitted from the nucleus, it collides with an electron around that atom, and then you have that annihilation reaction or process. And the importance of that is you make two photons. We talked about this. You make two gamma rays, and the thing is they shoot out in perfectly opposite directions. So when you do a PET scan, you put the nuclide in the person, and you put them in a PET scanner, which is a tube. This tube is covered in detectors for these gamma rays. And so because those gamma rays are emitted in opposite directions, they're creating an explicit line that would show you the point in space where that nucleus was when the emission happened, when the positron was emitted and those two gamma rays came out. So it's sending out this signal. This is the location of the nucleus. And so when you do a PET scan like this, so that'd be the image on the right, you can give some sort of radio isotope or nuclide that is unstable to emit positrons. And now you can get information not only on the structure of the organism, but you can also start to get metabolic information, right? As there are more of that molecule, where are the regions of it? So say you're imaging a tumor. On the right here, you can see all the internal structures, but you can also then see where there are more molecules, right? There are more molecules in this bright spot because it's a tumor, which is uptaking more resources. If you just do a CT scan, which is computed tomography, that's basically just a really fancy X-ray. And so you are sending radiation from outside the body and then bouncing it off of all of the parts of the body. And so that's really useful imaging, and you're still using radiation, but you're not using the fact that you have nuclei inside the body that are sending out signals. It's all about reflections, and it's all about bouncing off or going through internal structures. So when we want to do imaging, we're just trying to pick any radioisotope, right? But you can't just use anything you want. There are going to be specific requirements for what works best for different situations. So this table is all different types of radioisotopes that are used in different applications of imaging different parts of the body or different organisms or things like that. So you have all sorts of isotopes available, right? There's hundreds of possibilities for if you just want to find an unstable nucleus, but they're not all necessarily suitable for use in imaging. One of the things you need to be thinking about is, what sort of atom is going to be selective to a given organ that you're trying to trace. So the top two, carbon-11 and fluorine-18, those are both positron emitters, so they're used for PET scans. They also are incorporated into glucose molecules, so sugar. So if you put it into a healthy person, those glucose molecules preferentially go to the organ that uses the most glucose, uses the most energy, which is your brain. So you do need to know a little bit about some of the functioning of, say, organs. You can also use some other chemistry. We use iron isotopes to look at, say, bone marrow functions. So that'd be your blood vessels, so places where a lot of iron's present. Strontium is right beneath calcium on the periodic table, so you can use that similarity. The strontium will get into your bone, so if you want to do a bone scan, strontium would be a good choice. Iodine goes into your thyroid. So picking atom types that are in molecules that have certain preferential functions. You also need to know what to look for. You will note under the modes of decay, none of these are alpha emitters. One, the alpha particle wouldn't make it out of the body, and two, it'd be too dangerous, right? It would be doing a lot of serious local damage to whatever organ you're trying to image, right? So that's why we're using beta emitters, electron capture, positron, because there is some gamma rays that are going to come from that. Those can make it out of the organism or out of the organ and out of the body that you can actually look at them. But what we don't want to do is use alpha emitters where you're just doing a lot of local damage. If you also look, the other consideration, so you figured out you have an atom that's the right type to go to the organ you want. It's going to do a safe type of decay or a decay that you can follow. Then you need to figure out what has the correct half-life, right? You'll note all of these half-lives are generally on the order of minutes, hours to days. You wouldn't want something that has a half-life of seconds because if it's only in the matter of seconds, then by the time you say injected it into the person, it would have all decayed and it's not going to make it to the organ. If it's too long of a half-life, then what's the point? It doesn't, when it gets to the organ, it doesn't necessarily undergo enough decay for you to even see. You will note there is one here, krypton 81M, that has a 13.3 second half-life. This is really short, much shorter than everything else, and this is used for lung ventilation scans, right? So if you think krypton is a noble gas, so one, you have to use a gas if you want to see the ventilation of lung, where is air accessible inside your lung, and two, your breath is not, when you inhale, that's not a very long amount of time. So you need to use an isotope that has a pretty short half-life, right? 13.3 seconds. So that's why when all the krypton gets into your lungs, it's all emitting it's gamma rays that can then be observed. And then when you breathe it out, that also corresponds. You breathe it out after it's done, so you're not necessarily that concerned about any sort of lasting effects. There is going to be some deposition, but you are going to breathe it out mostly. So when it comes to picking these isotopes, there's a lot of chemistry, a lot of biology, and a lot of physics going into it. It's not just kind of, hey, pick something, pick a nuclide and inject it into someone. So, there's a lot of possibilities. You have all your different isotopes with different given atoms, right? Iodine, which isotope you want to use, what has the right type of decay, what has the right half-life, balance everything out. There's a lot of variables. There's a lot of nuance to this. It's not just kind of slapdash, throw in radioactive things into people, which is also a pretty dangerous. There's going to be damage. You want to make sure you're getting some good bang for your buck. So the other big usage of nuclear decay in medicine is in terms of therapy. And so we previously saw that radiation just causes damage, right? It can kill cells, kill living things. It can also be used to kill or damage dangerous tissue, specifically or largely with tumors. And so there are two main types of radiation therapy: external beam radiotherapy and brachytherapy. And so in external beam radiotherapy, you have an external radiation source, you shine it on the person, and then that is focused onto wherever the tumor tissue is, wherever the cancer is. And so that idea is generally always going to be based around a gamma type of radiation. The reason being, it starts outside the person and it needs to get in to wherever the tumor is. So it has to be able to pass through the skin, other organs, or get to wherever it is. And so with external beam radiotherapy, there is the potential, there's generally going to be a non-trivial amount of basically kind of collateral damage where you're affecting other healthy tissue. And that's why you can get, side effects from it and things like that. But there is, still going to be, you can focus the beam to primarily deposit inside the tumor and do that killing. So external beam radiotherapy always has to be gamma. When it comes to brachytherapy, the idea with brachytherapy is you take a radioactive source and you put it inside the person. So this would become an internal source. You put it inside the person close to the tumor. Here, you use an alpha emitter. So with brachytherapy, you would use an alpha emitter where you put, say, some sort of nucleus that's going to decay via alpha radiation or alpha decay right next to the tumor. So that way, all of those alpha particles are directly affecting the tumor. You can minimize the collateral damage or the side effects because it has to be, all the alpha particles get blocked right by that tumor. Of course, ideally, you're in the middle of the tumor. Usually, you only get next to a tumor. So that can cause some potential issues. But you can get really localized heavy-duty damage. And any collateral side effects are localized to that region where the tumor is. Unfortunately, with brachytherapy, the tumor has to be accessible to external, obviously, sources. So inside the lungs works. Prostate cancer is pretty common. Eye cancers, other skin cancers, you can use brachytherapy for, or you have to use surgery to then implant the sort of source and then take it out at a later time. So you are certainly limited in application. Gamma radiation, that external beam therapy, theoretically, you can access any organ using gamma radiation. Some are more conducive to, some types of cancer are more conducive to it, but you can certainly theoretically get anywhere in the body using gamma radiation. So more applicability, and brachytherapy generally potentially less side effects and more direct damage. You can do some really heavy duty damage using alpha particles on those cancer cells. Again, it's all about kind of understanding what the radiation is and how you want to use it for your given to decide what's best for your given application. Okay, no participation questions here. One more video in this set, maybe some questions in that one. Who knows? See you there.